Hello everyone, today let's take a look at QP160, just basically showing the memorylessness of the geometric in part A, and then in part B we're just going to basically derive the expected value and variance of the negative binomial distribution. So in part A we have x as this geometric random variable. Again, it represents the number of trials till the first success in independent Bernoulli trials. So show that for any integers m and k that basically the geometric distribution is memoryless, which is this property right here. So this is a pretty simple property to show, right? We're trying to show that the probability that x is greater than m plus k, given that x is greater than m, is going to be equal to the probability that x is greater than k. So let's just start with the left-hand side of this equation, use the definition of conditional probability, and arrive with the right-hand side. So the definition of conditional probability, which we've talked about extensively at this point, tells us that this is just going to be equal to the probability that both of these conditions are true, so both are true, and that's going to be the probability that x is greater than m plus k, and basically x is greater than m at the same time, and that's going to be divided by basically the probability of this right here, the probability that x is greater than m in general. So up here, first of all, the probability that x is greater than m plus k and x is greater than m, that's the same thing as just saying the probability that x is greater than m plus k, because in order for x to be greater than m plus k, obviously it's going to be greater than m, because obviously, well, m and k are greater than or equal to 0. And now let's just do the probability that x is greater than m. Let's look at that first. So what's the probability that in independent Bernoulli P trials, we basically have the number of trials until the first success greater than some value m? Well, this is pretty simple. The probability that the number of failures until the first success is greater than some fixed value of m is just the probability that for the first m flips, right, we all get failures. The probability of a failure in an independent Bernoulli P trial is obviously just going to be 1 minus p, so we just raise that to the power of m because they're all independent, right? That's the probability that x is greater than m. Now let's look at the probability right here that x is greater than m plus k. So the probability that x is greater than m plus k, again, we can think about it in much the same way. That just means that for my first m plus k trials, I get all failures. That happens with probability 1 minus p raised to the power of m plus k. So now that we know both terms right here, all we have to do is plug them in, right? So this on top is going to be 1 minus p to the power of m plus k, and then on the bottom, it's going to be 1 minus p to the power of m. And now properties of exponents, obviously this is just equal to 1 minus p to the power of m times 1 minus p to the power of k, and then these are going to cancel right here, and then this is just going to be equal to 1 minus p to the power of k, and wouldn't you know it, that is the probability that x is greater than k, right? So this is right here is the probability that x is greater than k. So that basically completes this proof. We just showed that the left-hand side is equal to the right-hand side, and this is the only discrete distribution where this property is true. The only continuous distribution where the property is true is the exponential. So the geometric and the exponential are kind of unique in that sense. That's why you see those two distributions in stochastic processes a lot, because of this memorylessness property. So what does it actually mean though? So all memorylessness is saying is that if you've been flipping m times and you still haven't seen a head yet, the wait time kind of starts again over fresh, right? The probability that you still need k more flips after these m initial ones is equal to the probability that you need k given that you just started flipping, right? It doesn't matter at what point that you come in at this process, right? Your probability distributions are still going to be exactly the same. And that right there is a pretty simple property to prove, right? It's the only discrete distribution that has that property. So now let's look at part B. Let's let y be a negative binomial Rp, denote the number of trials needed to obtain R successes in independent Bernoulli trials, and then we need to find the expected value and variance. So again, this one right here shouldn't be too complicated either. Y is distributed as a negative binomial with parameters R and P, where R basically represents the number of successes that we are trying to count, and P represents the probability of success on any given independent Bernoulli trial. So key thing to notice is going to make our lives a lot simpler. Since Y represents the number of trials in order to obtain the rth success, right? That's just going to be equal to basically the number of trials to obtain the first success, plus the number of trials to obtain the second success, plus the number of trials to obtain the third success, etc., all the way up to R. So again, to write that out more formally, we can just express Y as basically the sum of the number of trials to obtain the first success, plus basically the number of trials from the first success that it takes basically to obtain the second success, plus the number of trials that it takes from the second success to the third success, and then plus basically all the way up to the number of trials to obtain the rth success from the r minus 1th success. Now again, by linearity of expectation, which we've already proven, the expected value of y is just going to be equal to the sum of the expected value of this right here, plus the expected value of this right here, plus all the way up to the expected value of that, right? That's just linearity of expectation. But all of these right here are also just going to be geometric random variables, right? The number of trials to obtain the first success is going to be geometric with parameter p. The number of trials to obtain the second success from the first success is also going to be geometric with parameter p. The number of trials to obtain the rth success from the r minus 1th success is also going to be geometric with parameter p. Every single one is. So this right here is exactly analogous to the exponential distribution and the gamma distribution in the continuous case, which we'll talk about under continuous distributions, right? In both, we are quantifying the waiting time between successes, and the memorylessness property of each, right, allows for us to just sum them up in this way. So again, the expected value of y by linearity is just the sum of the expected values of all these geometric p's. How many do we have? We have r of them, right? So r times the expected value of a geometric p, right? And we already know what the expected value of a geometric p is, which we just proved in QP 123. That expected value is just going to be 1 over p, right? So the expected value of y is just going to be r over p, right? That's the expected value of the negative binomial. Now, the variance of y we can solve in much the same way. Why? Because everything here is independent. We're dealing with independent Bernoulli trials. So we know that y is just the sum of the number of trials to obtain basically the first, second, all the way up to the rth success, right? So the variance of y is just going to be the variance of that sum, right? Or the sum of the variances. Because in this case they are independent, we have no covariance terms, right? So we're just going to have to sum up the variances of a bunch of geometric p variables. How many do we have? We have r of them. We're summing up the variance of a geometric p r different times, right? So we just have r times the variance of a geometric p. What is that variance? We also proved it in QP 123. Is just going to be 1 minus p on p squared, right? So that's your final answer for the variance of y, right? Pretty simple. It's just going to be r times 1 minus p on p squared. So those are your final answers, some pretty similar properties. When we do the exponential and gamma distribution, you'll see how similar these two different distributions are, right? One for the discrete case and the other one representing time in the continuous case.